Okay, so if you're an engineering student, you definitely know this feeling. You're staring at a question about rock classification, just trying to remember the difference between stratified and foliated, or argillaceous and siliceous. It's a huge hurdle in exams for sure. But what's even crazier is that getting it wrong in the real world, that can lead to some catastrophic and I mean expensive failures. So let's dive into this and clear it all up for good.
Take a look at this. This is a classic question from a competitive engineering exam. It grabs one single rock and asks you to define it geologically, physically, and chemically all at the same time. I mean, it feels like it's designed just to trip you up, right? It blends three totally different ways of classifying rocks into one confusing puzzle. So, do you know the answer? Don't worry if you don't, because by the end of this, you'll be able to solve these in your sleep.
And this confusion isn't just some abstract exam problem. No way. This is the kind of mistake that has huge, real-world consequences. Just imagine this. You've specified a beautiful stone for a heavy-duty industrial driveway, only to have it start crumbling into dust just weeks later. It happens, and it happens because of a fundamental misunderstanding of the material you're working with.
So let's get into that story, that real-world failure. The story goes that a contractor used what looked like a really solid batch of sandstone for a driveway, but this driveway needed to handle heavy dump trucks. Well, pretty soon after, the surface began dusting, spalling, and then cracking completely. And the problem wasn't the foundation, it was the rock itself. A super costly mistake that all came down to a simple classification error. So what went wrong? Well, the contractor used sandstone, which is a sedimentary rock. That means it's naturally porous, and it's built in layers. It just couldn't handle that kind of load and friction. What they really needed was a tough, unstratified, crystalline rock, something like granite or basalt, which is formed under totally different conditions and has a much, much stronger internal structure.
To avoid these kinds of disasters, you need a system. And lucky for us, there is one. In engineering, we classify rocks using three fundamental pillars: their geological origin, their physical structure, and their chemical composition. You master these three, and you've pretty much mastered the entire topic. So let's break them down one by one. All right, first up, geological classification. This one is all about the rock's origin story. You know, where did it come from? How was it born? Understanding this is the absolute first step to predicting how it's going to behave.
So there are really three main origin stories. I like to think of them as fire, settlement, and change. Igneous rocks are born from fire. They're the original primary rocks of the Earth, formed when molten magma cools down. Sedimentary rocks are formed from these settlement of tiny weathered particles that get deposited and basically glued together. And metamorphic rocks? They undergo a complete change when another rock gets hit with massive heat and pressure, transforming it into something totally new.
Now, let's zoom in on igneous rocks for a second, because this is a favorite exam trick. As you can see, where the magma cools changes everything. Think about it. If it cools super slowly, deep inside the Earth, it has time to form these big, visible crystals. We call those plutonic rocks, and granite is a perfect example. But if it erupts as lava and cools really fast on the surface, the crystals are tiny. Those are volcanic rocks, like basalt. See? Same origin, totally different structure. Now for sedimentary rocks, the key process you gotta know is called lithification. You can think of it like nature's own cement mixer. Over millions of years, layers of sand, silt, and other stuff are buried and squeezed together until they form solid rock, like sandstone or limestone. And here's a golden rule for your exams. These are the only rocks that can have fossils, because the process isn't hot enough to destroy them. And finally, we have the great transformers, metamorphic rocks. When existing rocks get cooked and squeezed, their entire mineral structure changes. Soft limestone becomes hard crystalline marble. Sandstone becomes the incredibly tough quartzite. And soft shale gets compressed into flaky, layered slate. You absolutely have to memorize these pairings. Seriously, they are free points on an exam. Guaranteed. Okay, on to our second pillar, physical classification. This is all about what the rock looks like and, crucially, how it breaks apart. And this is where one of the biggest points of confusion for students comes in. And here it is, that big point of confusion, all in one question. Stratified versus foliated. I mean, they both describe rocks that have lines or layers, right? So what is the real difference? Because getting this right isn't just about your grades. It's about understanding if a rock is going to hold together or just fall apart under pressure. And this slide illustrates the answer perfectly. Stratification is from deposition.
particles settling in horizontal layers, kind of like pages in a book. Think stacked layers. It's the classic sign of a sedimentary rock, like sandstone. Foliation, on the other hand, is caused by immense directional pressure that forces all the minerals inside a metamorphic rock to line up in parallel bands. Think forced lines. It's not about deposited layers, it's about the internal alignment of the minerals themselves. And that's why slate splits so easily into those nice thin sheets.
All right, we're onto our third and final pillar, chemical classification. This is where we get down to the nitty-gritty, the molecular level of what the rock is actually made of. This chemical blueprint is what determines its hardness, its durability, and its resistance to stuff like acid rain.
First up, we've got siliceous rocks. Their main ingredient is silica, sand. And silica is incredibly hard. It's a 7 on the Mohs scale, which makes these rocks the absolute toughest and most durable building materials you can find, perfect for things that just have to last, like a bridge foundation. So the key examples to lock in your brain are granite, quartzite, and basalt. Now, what's really important to notice here is that these examples, they come from different geological families. You've got igneous and metamorphic rocks all in the same chemical group. That's exactly why you can't just mix and match these classification systems. Next up are the argillaceous rocks. Their main component is argol, which is just a fancy word for clay or alumina. Now, these rocks, like slate, can be pretty hard and durable, but they've got a major weakness. They're brittle. That means they can't take a big hit, and since they're clay-based, they can also get damaged by moisture.
Besides slate, which is definitely the star of the show in exams, you also have laterite and kaolin. At their core, these are all fundamentally clay-based rocks, and that's what gives them their unique properties.
And finally, we have calcareous rocks. The main ingredient here is calcium carbonate. Generally, these rocks are softer and way easier to work with, which makes them perfect for ornamental work and detailed carvings. But here's their big weakness: acid. If you put even a drop of weak acid on them, they'll literally start to fizz as the calcium carbonate reacts and releases carbon dioxide gas.
The two classic examples here are limestone and its metamorphic kid, marble. And that chemical property is exactly why you would never, ever use marble for the outside of a building in a place with a lot of pollution and acid rain. It would literally dissolve over time. No joke.
Okay, so we have our 3 pillars. We've built the whole framework. Now let's put it all together and see how examiners use this information to create some really tricky questions, and more importantly, how you can see right through them. This table right here is your ultimate cheat sheet. Just look at slate. It's metamorphic, foliated, and argillaceous. It hits a unique keyword in every single category, which is why examiners love it. Now look at sandstone. This is a classic trap. It's sedimentary and stratified, right? But chemically, it's siliceous because it's made of sand. So many students wrongly assume it must be calcareous like limestone. Understanding these full profiles is the absolute key.
And here is a super practical rule that you will almost certainly see on an exam. When you're using a stratified rock like sandstone in a wall, how do you place it? The crucial thing to remember is that the bedding planes, those natural layers, must be placed perpendicular to the load. Why? Because if you place them parallel, the rock will just split apart under pressure like a deck of cards.
So we end right back where we started, with the difference between a rock that looks right and a rock that is right. Whether you're in an exam hall or on a construction site, the principle is exactly the same. True engineering skill isn't about just looking at something. It's about understanding the origin story, the internal structure, and the chemical blueprint of your materials. So the real question is your foundation built on the right knowledge?